This is the first workshop for the ReTune Early Career Committee, and ReTune is the transregional SFB funded by the DFG. And my group is part of project B3 and also of the informatics project. And ESTA is part of C1. And together we have the honor to give you some insights that we have gathered over the last years on how to deal with intracranial LFP data. So the requirements are to have Matlab or Python and Anaconda. If you want to follow everything, you need both. And here are some GitHub repositories that are required. And you will see more about this during the following slides. But let's start with some very basic introduction on why we are interested in this. And over the past years, a lot of research has shown that it is possible to record specific patterns of LFP activity in different patients with different disease entities, and this has some potential clinical value because it could be possible to use such patterns to change the stimulation or adapt the stimulation, and also to learn about the pathophysiology, about the disease mechanisms underlying the symptoms that we can see in the clinic. So for deep brain stimulation, electrodes are implanted into the depths of the brain, into different nuclei. So that's what we call a DBS target. And you can see on the top here, a figure created with the DBS, where an electrode is traversing the frontal lobe into the depths of the brain. And here on top, you can see the thalamus, and down here, you can see the subthalamic nucleus. That is the common target for Parkinson's disease. Now, depending on the clinical center, on the disease type, some people also implant, or doctors also implant in the internal pallidum in Parkinson's disease. But in our clinic, mainly, if we implant into the internal pallidum, shown here in pink, that is for patients suffering from dystonia, so a different disease entity. In essential tremor patients, we often implant in the so-called ventral intermediate nucleus of thalamus. So there are different deep structures that we implant in depending on the DBS indications, so the reason why we implant the electrodes. And it is good to know some of the anatomy to really understand the relationships of the recordings that we get from these electrodes. And depending on the depths, it is, for example, possible to, in the GPI trajectory, to record additional GPE, and sometimes in the SDN, on the uppermost context, you also have some thalamic activity. So it's good to know where exactly the electrode was, even if we don't look at that during the LFP analysis. Now, in addition to just LFP, there are opportunities to combine these recordings, and Esther Thurin is particularly experienced in such recordings, where, for example, you can have whole head MEG during the LFP recording, and then you can look at specific network activity or network coupling modes that can be different between Parkinson's disease and dystonia, or between subthalamic nucleus and internal pallidum. So that is still an ongoing research, and there are some dedicated projects on that in the ReTune CRC. Practically, what we need is an externalization extension when we record in the period after the electrodes are implanted, but the pulse generator is not implanted yet. So that is the typical setting in which we, in Berlin, record LFP. And you can see here an exemplar DBS lead, and then you have this externalization extension that the neurosurgeon implants. And in the lab, what you need is basically some adapters to be able to connect to this externalization extension, and that depends on the specific manufacturer of the DBS leads. So it's different for Medtronic or Boston Scientific or Abbott. And then you will likely have some kind of connection adapter to your electrophysiology head stage. And that, in our case, is often a touch-proof adapter, a standard EEG connector. In addition to the DBS lead itself, you always need a ground electrode to make sure that you can get rid of noise from the room and from the power lines. You use a recording computer that is connected to an electrophysiology processor, and then you can get some beautiful LFP activity from different recording contacts in the DBS lead. Now, additionally, of course, you can also add some EEG, ECOG, or other kinds of modalities to your recordings. And in Berlin, we have started to record ECOG in some patients. In addition, we often actually almost add at least minimal EEG electrodes on top of the head to get some cortical activity too. And often we also record some EMG. Now, what you see here is exemplar real LFP activity that is already referenced as a bipolar in between adjacent contacts. So that means what we see here is really local activity. It is the difference of voltage that we record from this channel to this channel. And what you can see nicely here is that in the topmost contact pair, there is the highest level of higher frequency oscillations, or in this case, it's the low beta range. And that means that you can see that the activity that we see is really local. It's not here, but it's in this channel only. And often, you only have one reference. So to get to this stage, there is some manipulation of the data required. And that is even more complicated when we talk about the different kinds of DBS electrodes. And not all electrodes are the same. The previous example was a standard Medtronic kind of electrodes that you can see here. It has 4 contacts and it's relatively easy to handle for LFP. But there are also often nowadays Boston Scientific directional leads implanted, or also the Abbott directional lead, and or the longer Boston electrode. So there are 2 things to note here. One is that not all leads are the same, and the amount and amplitude of signal that you will get really depends on the impedance and the size of the contact that you have. The larger the contact, the lower the impedance, the higher the amplitude that you get, or bigger the electric field that you cover. That means that in these smaller contacts, you may not get the same amount of signal in the when you record compared to these larger contacts. And the other thing is that even if you have just 4 contacts that are ring contacts, so not segmented, depending on the actual size and distances or spacing of the contacts, you will cover a completely different amount of neural tissue. So this will signal that I get from these adjacent contacts will be smaller in amplitude, but also more focal in tissue when compared, for example, to these, I think they are for spinal cord stimulation, these large contacts, the spacings. Okay, so ultimately what we do is we connect, for example, some of these DBS electrodes, maybe an additional ECOG strip and some EEG electrodes to our outbreak box of our electrophysiology processor. And this is what we use, the current system. And this is a TMSI Saga device where we would try to connect every single of these contacts with an adapter to these inputs. And this can be quite complicated, and I have visualized this a little bit here. And let's start with an exemplar setup where we have standard Medtronic 3389 DBS lead, and we have that in both hemispheres. Additionally, we have such a 4-contact ECOG strip and some EEG and EMG on the head and the arms. So left is left, right is right here. We need to connect all of these contacts to our input box. So we would start in our, this is how we do it in Berlin, exactly how we do it in Berlin. We would start to connect all right electrodes contacts to the first inputs of our output box. And then we would follow up by the left inputs. And here you can see the last input here is empty. And that is because for all electrophysiology recordings, you need a reference, which means that you are recording the voltage of a signal compared to a different voltage. Or, so you're recording the difference in voltage to a common reference. Most electrophysiology processors require this, not all of them, but I think it will be the standard, what you will notice in your settings. And what we use is LFP channel. We basically sacrifice an LFP channel as a reference to make sure that we have a reference that is similar in terms of the impedance to the other contacts of the LFP. If you, for example, use a different electrode, it may contaminate more of your signal. For example, if we would use an ECOG electrode, we would see a lot of ECOG activity in every single of the LFP channels. That is because the ECOG electrode has a lower impedance and much higher signal amplitude. There's ways to deal with this, but we prefer to, and many others do so too, prefer to use a DEPS electrode or LFP channel as a reference. Also compared to an EEG electrode, this channel will not disconnect when the patient moves or like pulls the strip or something like this. But nevertheless, it can be prone to artifacts that come from movement. Anyways, this is very important, and we will get to this a little bit later again. We would connect our ECOG electrode to inputs like 8, 9, 10, 11, and we would have an additional, for example, EEG electrode on the motor cortex C3 and CZ to be able to derive some bipolar recordings. And depending on your specific setup, you have maybe an EMG electrode that you could either connect here, or you may have additional strict bipolar channels as they are implemented in the TMSI saga. Then you don't need to connect and reference them to the LFP. Again, you have the ground signal, and that is how we would set up the whole thing. And to really make sure that you understand this referencing thing, I wrote this down here. The first channel would be the right lowermost SDN LFP contact, reference to the contact 3 of the left electrode. And the same is true for the next channel for SDN R1, same for SDN R2. So it's always, for all these inputs, it is a combination, the signal is a combination or the voltage difference between your channel of interest and the reference. So practical rules of thumb, connectors and adapters, as I have shown here, these connectors that are depicted can always be a source of
I have a question.
Yeah.
Is okay to this. So you mean you digitally subtract it, or you actually change something in the hardware configuration that it becomes the actual reference for the amplifier?
So I don't change anything, but the hardware expects a reference. So there's no other way, basically. You need to add a reference in the hardware to record. Mm-hmm. So the hardware subtracts it.
Okay.
Another way to do it is to record common average reference. Some hardware can do that, and the TMSI Saga can also do that. You can choose in the software the setting that you don't want to add an additional reference, but you want the common average signal to be the reference. But I would advise not to do that, because then it's a really strange mix of signals when you have EMG, ECOG, and STN all together. It's a good choice if you only have 64 EEG channels and they all have the same impedance and they are basically the same signal type. But as soon as you mix different impedances and electrode configurations and sizes of the contacts, it can be a mess what you get. And also sometimes it doesn't work because the reference difference is the difference of the reference from common average to the signal itself can be very high.
Can I also ask a question? Sorry. Yeah. I'm not very experienced with all these recording techniques, but why not, for example, use the earlobe as a reference? Because we now referenced the right STN to the one of the left STN electrodes, and I don't understand why we want now the left STN signal basically in the right hemisphere. Wouldn't the earlobe, for example, be a more neutral reference?
Yes, so it's possible to do that, and some people do it. I don't like it because it is a very unstable signal. So it can disconnect, especially in the earlobe. There's this tendency for the electrode to drop or lose contact. Also, depending on the skin impedance, you can have variance in terms of the actual impedance of the signal. And additionally, in general, you would like your reference signal to have a very similar biological surrounding and a very similar impedance. So that's why I don't like it. But maybe Esther can comment from her experience on that.
Yeah, so actually, when we do the MEG recordings, we do place our reference on the mastoid, which allows us to later do a re-referencing. But of course, if we always have to check at the beginning, because if we didn't get a good contact there for the mastoid, we cannot measure any signal in the end. So, and also we need to make sure that we don't lose this electrode throughout the recording, because then, yeah, it just would be gone basically. So, yeah, we decided for this because we didn't want to lose basically one channel, and we have these directional contacts where it would also not be so clear how to re-reference. I mean, if you have all the same contacts, it's quite straightforward to think that you do all bipolar, but how would we, I mean, the re-reference or for the starting referencing for the directional leads would also be a bit different then. So I see the point of using one channel because it can save you a lot of hassle, but yeah, we decided for the other option basically in the MEG.
Yeah. Okay, that's. I think that basically shows you that this is a choice that every lab has to make and make some experience from it. For the directional contacts, for example, I would be afraid that the signal of the mastoid is much larger than the signal of the directional contact. But then you can re-reference those again, and so yeah. I think there are many answers and many ways forward, and to do that.
No,
so
I mean,
I personally have bad experience with losing the reference, and then the whole recording is gone, basically.
Yeah, I mean, you definitely, if you record with the mastoid as a reference, you need to re-reference, because otherwise you will, when you look at our data at first glance, they look very similar because the mastoid signal is simply stronger. So you need to get rid of it, and this you can do by re-referencing. But that is, of course, a risk because you cannot see during the recording as clear if every channel is actually doing or recording what you expected it to be recording.
Right. Yeah, that's a good point. So in addition, during the visualization of your recordings, if you primarily see the reference, you don't know if you actually record anything from your contact of choice. But that's also true if you use a LFP channel. That is good. I think it's like a whole philosophical thing that you can go into, and you can always ask me or Esther how we feel about certain setups. I think we are both open-minded and thinking, depending on what exactly you want to achieve, there's a good way forward. Okay, so
Sorry, and I think there's one other question.
Yeah, sure.
Should I go? Okay. And what, I think I missed this, but what happened to the difference between the voltage between adjacent contacts? So all the different pairs, 0, 1, 0, 2, and all that stuff?
We don't have them yet. This is how we, as I mentioned before, to get there, to get this difference, we will have to re-reference. So we'll have to do additional calculations to get those, and we're going to go through this in practical. But for now, we have recorded this, and we don't have any adjacent differences. We only have the difference between contact 3 from the right hemisphere and all the other contacts.
Okay, thanks.
Left hemisphere, sorry. Okay, so some practical rules of thumb, or another question?
I think there's Konstantin also that has a question.
Sure.
Yeah, hi, can you hear me?
Mm-hmm.
Okay, great.
Yes.
So you have shown us different electrodes, and some of them had those segmented contacts on one level. So my question would be, so intuitively, I would think that due to the higher impedance, the measurements would be more localized. So the question would be, when you measure local field potentials with these electrodes in the STN, do you actually see a more characteristic response of subregions of the STN? So for example, if we think about adaptive DBS, would it be better to control the stimulation, or the signal is just not enough to characterize?
Yeah, so that is a very great question. And that's currently where the research field is working. So Esther has some current upcoming papers on similar questions, but there are also some papers already published on differential directional recordings. It is, I would say, still very difficult to answer because, first of all, there's a question whether the anatomical representation is so different in between these very localized contacts, and I would argue that it's not. If you look at the anatomy of the subdynamic nucleus, you can see that the neurons span the entire nucleus. And of course, there's different inputs, and there's probably different parts that you can record. And there are different kinds of or strengths of certain patterns, but all the groups that have tried, including us, to get like a signal that is, for example, somatotopical, has a somatotopical representation of hand versus foot movements or arm movements. This fine-grained difference is currently not seen in these recordings, I would say, but still there are differences in there that will need further research. So Esther, maybe you can comment what you found.
Yeah, so I mean, we basically also tried to see whether we find a distribution of beta activity for the different contacts. And yeah, our conclusion so far is that there is not, if you are staying on one height, there is not a really clear it's not really clearly distinguishable. And it's not even the case. I mean, many patients in our clinic are stimulated via one of the directional contacts as the best clinical contact, but we could not see that this particular contact would then show a very specific pattern why it was chosen. So, well, there are many reasons why we couldn't find it probably, but I would also argue that it's not so straightforward and maybe also not as localized the recording as one usually thinks it is.
Yeah, one thing that we should add, especially as this is the more practical oriented workshop, is that whenever you have a higher impedance electrode, it is more difficult to get a good signal. So the LFP that we are recording are extremely low in amplitude compared to EEG or cortical activity. And with the higher impedance of the small contacts, to make it even more difficult to capture it. And then relatively other signals can contaminate these recordings. And for example, for the Boston Scientific directional lead, it is sometimes really difficult to get a signal at all that is not completely contaminated with cable movement artifact. So every tiny movement of this cable can be seen in these small contact recordings, because the signal itself that we record is so low in amplitude that everything else really stands out. So I would say that overall, these directional leads did not help LFP research a lot. Instead, they made it more difficult. And Medtronic is coming out. Medtronic has this implantable pulse generator that can also record LFP, the Medtronic Percept device. And they have announced directional lead since many years now. And from what I heard and what I can imagine, the reason why it has not come out just yet is that it is super difficult to create an electrode that is both like directional and still has reliable capability to capture LFP.
Hey, Julian?
Yeah?
I think they have segmented leads now.
It is out now?
It is out now, yeah. I have the specifications.
Okay, but are they out is it possible to implant them now?
Yeah, so they are called Sensite. They have a slightly different marker, and Andrea told me that we are even already starting soon with that. But
that's awesome. Okay, so I wasn't up to date to the latest point. Yeah, but it definitely took a long time to get them into a stage of where they are capable to record LFP, and I'm looking forward to see whether they actually perform better for recordings than previous generations from other people. So Andy, can you tell us, is it going to be an 8 contact or 16 contact electrode?
8 contact as well. I thought 16, but it's the same thing. It's very similar except for the marker to the normal Boston, and it also has 3 mm spacing and 2 mm. So 2 different
versions. So it's basically the Abbott electrode.
Yeah.
Okay. So let's move on. Thanks, Andy.
Maybe we can have for Nakib's question short time, but I also need to say that the schedule is quite packed.
Yeah.
So maybe it's good also to have private questions.
Yeah, a very quick question.
So if you have like a question that is not directly related to practical questions of LFP recordings, but rather like in the future or something like ideas, please post them in the chat, and we can answer them later. I think for now we have to move on a little, because it will take more time to get into the Matlab stuff and practical hands-on stuff. Sorry about that. So I want to definitely want to get out these practical rules, because I think they can be very helpful. If you try to record LFP and you have a bad signal, check your connectors and adapters, because they are most commonly, in our experience, the source of a bad signal quality. And it makes sense to check and replace those adapters regularly, even though they're quite expensive. If you feel that over the last 3 recordings you always got a bad signal, a noisy signal, these connectors and adapters and cables in general can be a source of that. Then and that's true for any electrophysiology research, turn off any unrequired electric device to reduce 50 Hertz noise. And in our lab, I go in and plug out anything that is in the wall, like really anything. We record with LFP on a laptop. Our device is battery powered. And if you have a device that is not battery powered, that's fine. You have maybe I'm not even sure if the last version of ours is battery powered. It can be. But anyway, so only keep in anything, the one thing that is required, and do not load your, for example, your phone charger. If I see a phone charger in the wall, I would automatically plug it out before a patient comes into the room. Then ground and reference need to be good. Otherwise, all signals are bad. And that's what we discussed about, for example, mastoid or earlobe reference. If that disconnects at some points, you will not be able to recover any part of your recording from the time point on the reference lost touch. And of course, also the ground should be a low impedance electrode. We use patch electrodes on the shoulder of the patient, but often also these hand or arm or wristbands can be good. If you get a bad signal and your reference is good, try again to wet the ground or try a different ground electrode. That has often rescued for us the signal. Then the last thing that we discussed already, smaller contacts have higher impedance and therefore smaller signals. So that is expected, but can also create some problems. Also when re-referencing, for example, if you want to re-reference a small versus a large contact, you will be left with almost only signal from the large contact because the impedance was lower and the signal amplitude is higher. All right, so we're going to switch to the practical part now. And I will open Matlab.